In the first section of this week, we'll be talking about conditional probability. And like I mentioned in the introduction, conditional probability is really just based on the premise that we want to be able to revise our probabilistic models based on new information. As we identify things that have occurred, we want to be able to go in and say, well, how does that affect the odds? How does that affect the probability? So we'll start out with conditioning by looking at an example, and let's assume that we have some sample space omega, and within that sample space we have a number of possible outcomes. We'll say that there are 12 in this area, and that all 12 of those outcomes are equally likely. Within this sample space we also have two events. We have the event A and the event B, and the event A has 8 outcomes within it, and the event B has 4 outcomes within it. And our goal at the end of the day is to look at this and say, how can we graphically establish this concept of conditioning, establish this way to revise our predictions based on new information? So the first thing we're going to do before we get too far into this is just find the probabilities of A and B. And this will require going back to lecture 1 if you don't remember the exact concepts behind here. But the probabilities are pretty simple in this case because we have equally likely outcomes. So the probability of A in this specific situation is just equal to the number of outcomes within A divided by the total number of possible outcomes, which we'll find is just equal to 8 over 12. Now, the probability of B is, again, very similarly, just the number of outcomes within B divided by the total possible number of outcomes. In this case, B has 4 outcomes, so the probability of B is equal to 4 divided by 12, which again, there's 12 total possible outcomes in our sample space omega. A question we might ask is, hey, we know that B occurred, right? Whatever this B is, this event, we know that happened. So now that that's happened, what's the probability that A also occurred? There's a area here in the middle that is the probability of A intersected with B, and that area is the probability that both A and B occurred. So we know that B occurred. What's the probability of A? In this specific situation, we can go through and say, well, in the case of B, there were 4 possible outcomes. We know that there are 2 possible outcomes within this intersection area, so the probability of A in this case, and we'll write given that B has already occurred. There's some new notation for you. We'll come back and look at this in a little bit more detail. But the probability of A, given that B has already occurred, is just equal to 2 out of the 4 possible outcomes within that event B. Now, the other side of that question is maybe A happened first. So if we know that A occurred, what is the probability of B? And in this case, we can look and say that the probability of B, given that A has already occurred, is equal to, again, just this ratio. So in A, there were 8 total items, but there's 2 here in the middle. So we can say that the probability of B, given that A has already occurred, is just 2 out of 8. Now, something to look at here that's kind of important is we're really looking at the ratio of the intersection here, this A intersect B, over the total number of events in the event that already occurred. And we're going to look at that here in just a little bit as our definition of conditioning. But if we look at this in a slightly different way, let's go back to that second question. We say that B occurred. What is the probability of A? Well, again, here in the middle, we have the probability of A intersected with B. In this area, we have 2 total events. In B, we have 4. And in A, we have 8. There are 12 total events. So if we were to look at, say, the probability of A, we already established on the previous slide that that is equal to 8 out of 12 as long as these outcomes are equally likely. The probability of B was equal to 4 out of 12. And then we can also say that the probability of A intersected with B is equal to only 2 out of the 12 total outcomes. So if we were to look at, again, this conditional probability concept, we could say that mathematically speaking, the probability of an event occurring based on another event occurring, let's say in this case that we're looking at the probability of B occurring based on A occurring, is just the ratio of this area here in the middle over the total event space. So we could say that the probability of A, given that B has occurred, is really equal to the probability of A intersected with B over the probability of B. And let's see if that math holds up. Again, we said earlier on the previous slide, just graphically looking at this, that it was 2 out of 4, or 1/2. And in this case, we'll end up with the ratio of these two values we already found. So it's 2 over 12 divided by the probability of B, which is 4 over 12. Well, the 12s cancel, and we're left with, again, 1/2. Or that 2/4 that we had from the previous slide. So this equation here that we're looking at, this probability of A intersected with B divided by the probability of B, we'll find is the actual definition for conditional probability. So we'll go ahead and write that down and make sure that we remember it for the future, that the probability of A, given that B has already occurred, is just equal to the probability of A intersected with B divided by the probability of B. So let's take that knowledge and apply it to a few examples. So the first example, we'll say, assume that there are 2 coins, and each of those coins has a probability of selection of 0.5. And we'll further say that coin A has a probability 0.2 of being heads, and coin B has a probability 0.8 of being heads. The first question we might ask is, what's the probability of getting heads? And using one of the things that we looked at from last week when we were looking at counting, we can just use the basic counting rule and say that we have 2 sequential events, and when we have 2 sequential events, we just multiply those together in order to get the resultant probability. In this case, the sequential events are the selection and then the probability of heads. So in this case, we have a 0.5 selection on each side, and then we have a 0.2 or a 0.8 depending on which coin is selected. So in this case, the probability of heads would just be 0.5, my probability of selection of A, let's say, multiplied by 0.2, which would be the probability of A giving me heads. And then the other way I can get here is that I select B. So then I would add those together. I get 0.5, which is the probability of selecting B, and I multiply that by 0.8, which is the probability that B will give me heads. And when I multiply these together, we find that that equals 0.5 as a probability. So the probability of getting heads without knowing which coin is going to be picked is just equal to 0.5, or 50-50. Now, the point of conditional probability is that we can use new knowledge to influence our ultimate decision, to influence our models, our probabilities, our expectations. So the question we might say is, hey, what's the probability of heads if we've already selected coin A? Well, we have that information already. It's just 0.2. So this right here is just a way of showing that new information can directly influence our model. Knowing that we selected coin A shows that there is a change in what our expectation is. If we didn't know that coin A was selected, we'd have a probability of heads of 0.5, but because we know it was selected, we have a probability of 0.2. And as you may notice, those are not equal. So conditional probability gives us the capability to update, to get new information. Another example might be a four-sided die. And this is an example that we looked at back in lecture 1, But assume that we're rolling it twice, that each side, 1, 2, 3, and 4, has an equal probability of occurrence. We'll say that the first roll is going to be, the value that we get on the first roll is going to be X, and the value we get on the second roll is Y. And then kind of similar to before, we'll say that we have this A that is the minimum of X and Y, and B that is the maximum of X and Y. So the first question we might ask is, what's the probability that B, our maximum of X and Y, is equal to 1? Well, if we look at this graphically, that's just this one place here. There's the maximum equal to 1. And as you may notice, there are 16 total outcomes, possible outcomes in this situation, and only one of them that is valid. And this, again, if you're not sure where I'm getting that, you might want to go back and review lecture 1. But this right here, we're looking at 1 out of 16 possible outcomes. So the probability that B is equal to 1 is just equal to 1 out of 16 possible outcomes, or 1/16. So let's say that we want to find the probability that B is equal to 1, given that A is equal to 2. Well, A is the minimum of X and Y. So the minimum of X and Y is anywhere that X and Y are both 2. That's an easy analysis. And then anywhere that X is equal to 2 and Y is something greater than 2. So that would be those two squares. It's also anywhere that Y is equal to 2 and X is greater than 2. Again, we're concerned with the minimum. So when all is said and done, we're left with those 5 squares. Now, if we wanted to find the probability of A equal to 2, again, that's our condition here. And as you can see, our condition is the denominator. So we will need that. We can say that the probability that A is equal to 2 is, since these are all equally likely, just 5 out of 16. Now, it's important that we check this because in order for this equation to be valid, for us to be able to calculate this conditional probability, this probability of B has to be non-zero. If it's 0, then we have an undefined expression. We can't calculate it because we have a 0 in the denominator of a division. We can't do that. So knowing that this is non-zero is important. Now, the second thing that we'll need to look at is the probability of the intersection of both the thing we're trying to check, this B equal 1, and again, our condition that A equals 2. Now, the probability of A intersected with B, or for this example, B equaling 1, intersected with A equaling 2, well, we'll need to find out what that is. So we already know the probability of A equal 2, and again, that's just these 5 squares. But what's the probability that the maximum of X and Y is equal to 1? Well, there's only one square where that can take place, and that is where both X and Y are equal to 1. Anything larger than that, like this square, for instance, we would say that X is greater than 1. It's 2, and so therefore the maximum would be 2. So in this case, we have a bit of a problem. We have 2 disjoint sets. We have the set B equal to 1, which is, again, just this set down here. And then the set A equal to 2, which is all of this area here. But the intersection of those 2 sets is 0. There is no intersection. So therefore, the probability of the intersection of those 2 events is also equal to 0. So we now have both arguments here. We have our probability of A intersected with B and our probability of B. But what we find is that the overall probability here, the probability of B equal to 1, conditioned on A equaling 2, is equal to 0 over 5/16, which is just equal to 0. So in this case, we have a probability of 0, that B would equal 1 if A already equals 2. And that makes sense because there's no way that both of those can be true at the same time. Now, if we look at an example where there is overlap, let's say that we have the probability of B equaling 3 when A is equal to 2. Now, in this case, we can still use the same A equals 2, which is that the minimum is equal to 2, and that is these 5 squares like we determined earlier. So finding this probability in the denominator is not a problem. It's still the probability of A equaling 2. So we can say that P of A equal to 2 is equal to 5 over 16. Now, where we run into a different scenario is the probability that B is equal to 3. So this is anywhere that both X and Y are 3, so the maximum would be 3, that X is equal to 3 and Y is something less than 3, so that would be these 2 squares here, and then that Y is equal to 3 and X is something less than 3, so that would be these 2 squares here. So we have 5 possible squares for that intersection. So if we look at the numerator here, we have that the probability of B equaling 3 intersected with A equal 2, well, it's not 0 this time. There are 2 total squares. So we have this square and this square where those both hold together. So we can say that the probability of those 2 events both occurring is equal to 2 out of the 16 possible events. So now to find the probability of B equal 3, given that we already know that A is equal to 2, we can simplify this. We can say that this is just equal to the probability of our A intersect B, which we determined was 2/16, or 2 out of 16 possible outcomes, divided by the probability of B occurring on its own. And in this case, B, our condition, was just the probability that A equals 2, or 5/16. So if we substitute that in, we have 2/16 over 5/16. Well, the 16ths cancel because they're in both the numerator and the denominator. And what we're left with is 2 over 5, or 0.4. So in this case, what we've shown with conditional probability is that if we know that the minimum of these 2 rolls is equal to 2, there's a 40% chance that the maximum is equal to 3.